Hello, everyone. I hope we're all keeping well, enjoying the conference so far. I'm going to be talking about some ongoing work with my supervisor. It's still early days, still working through some things. And we are primarily looking at we're looking at a couple of different applications of type theory. In particular, we're looking at using type theory for program specification and for natural language semantics. There's been a whole body of work that's previously been done on using primarily impredicative type theories to enable these applications. And we really want to look at whether or not it's possible to use predicative type theories, in particular Martin-Löff's type theory for these purposes. But there's a couple of problems where, because Martin-Löff's type theory is inherently predictive, there's a couple of different issues we need to work with and or work against, rather. It doesn't have both the weak and strong existential as an example, which ends up causing a couple of problems when we want to do certain applications. There's also a problem that I'll address later on, the counting problem, where you start talking about the cardinality of types that can also start causing problems. And if we want to properly use MLTT for these applications, we need to try and work out a solution for these. So our goal here is we want to make some small extensions, a couple of changes, and hopefully we'll be able to use MLTT for these purposes. Just as a quick side note, we are talking about Martin-Löff's intuitionistic type theory. There's no function extensionality. There's no other bits and bobs that we're adding onto this. So let's start addressing the title of the talk, equality reflection. We're interested in weak equality reflection, but there's two different types of equality reflection, and it's important to address the distinctions between the two. So the first type of equality reflection, probably the one that's maybe more familiar for most folks in the audience, is strong equality reflection. This is kind of an active process. We are enforcing propositional equality to be reflected onto judgmental equality. You might have an example of this, might be the inclusion of such a rule in your type system. This is a little bit brute force, but it gets across the idea that we want to try and conclude judgmental equality from propositional equality. Whereas with weak equality reflection, this is more of a passive process. We are saying that they just happen to coincide, these two different notions of equality. So you end up having you want one of these two rules, depending on what kind of equality your type theory is using, to be admissible within your system. And when you have weak equality reflection, you don't necessarily have a way to transition from one notion of equality to the other. You are working with something that's more a sort of external property rather than internal property. There are some well-studied type theories that do have weak equality reflection. MLTT itself is a good example of this, as well as UTT and others. But there are other type theories which don't have weak equality reflection. Traditional homotopic type theory, as described in the hot book, is quite a good example of this. There is an example which I swear is due to Mike Schulman. I've tried my best to find where he's actually written this down. I cannot for the life of me find a source for this. So if any of you can help me on that front, that would be fantastic. But the idea is quite simple. We take the circle and we can conclude that despite the fact that these two different equality paths that we've defined for the circle are, I mean, they should be the same, or they should be, how do I word this? The identity type for the circle should be a mere proposition, I believe is the right phrasing. But these two different objects are constructed differently. And so we kind of want to be able to conclude that they're judgmentally distinct. But that isn't necessarily the case. I'm going to start talking about applications. I hope this is probably the least controversial statement in my whole presentation. We could use type theories for programming. That's quite a fun application. We can have a program specification as some pair, a type plus some predicate on that type, and we can use this to describe sort of expected behavior for whatever function, whatever programming that we want to describe. So here's some brief examples. Weak equality reflection is quite important for these applications because we want to be able to describe the expected behavior of a program rather than trying to prescribe some behavior to it. So, I mean, a common example that we might be able to cover here is bubble sort, merge sorts. They're both sorting algorithms. The end result should be the same. We don't necessarily want them to be the same function. We don't want to describe these two functions as equal because we may want to specify, we might want to analyze the differences between these two functions in, for example, running time. We can also use type varies for natural language semantics. This is quite a well-studied area. Primarily, initial work was done in the 1970s. I may be wrong on that. Primarily working from Church's simple type theory for prescribing meaning to natural language. And there's been some recent developments in the last 20 odd years on using dependent type theories for this exact purpose. So if we were to go through a simple example, Peter owns a cat. We can turn this into a type. And then any object of that type would be sort of a witness of its truth or of the information that the sentence contains. So here we're using Sigma, which is quite interesting. Peter owns a cat. We're not talking about a specific cat. Part of the reason for this is when we're working in MLTT, we only have access to the strong existential. This is kind of problematic because the Sigma plays two different roles. We can use this to start talking about subset construction or propositional subtyping, for those that are familiar with that. But we also want to be able to use it as an existential quantifier. And the fact that it plays both of these roles can cause a couple of different problems. There's a good example of this in a talk given by Escado, where he talks about the fact that when you try to, for example, define the image of a function in MLTT, you end up with this weird property that the image of the function is, what's the word, type isomorphic to its domain, which is not really a property we necessarily want. It feels weird to have, for example, if you have a function that projects from Booleans to the unit type, it's weird to say that the image of that function is the Booleans. That's quite bizarre. So going back to natural language semantics, there's an interesting example of the application for this, where we can start talking about adjectives. We can prescribe some meaning to adjectives. This has been quite well studied, initially proposed by Monica and Sundholm in two different papers. And the idea is we want to use the Sigma type here. We want to represent, here is some noun that we can prescribe some proof to of some description. Here, we're using this predicate to represent the adjective that's acting, it's describing whatever object we might be talking about. Another quick example, if we want to say there was one black cat in the garden, then the correct semantics for this might be, maybe, hopefully, there's an issue with this. I don't know if anyone can spot this immediately. What if we have more than one proof? In which case, you know, if I have two different people look at the garden, one person concludes there's a black cat, the other person concludes there's a black cat. Conclusion, there's two black cats. That doesn't really make sense when we're trying to prescribe meaning to that sentence. So we want some notion of proof relevance in our system so that we can ignore the fact that we might have two different proofs of the same property. So the idea is that we want to try and add in proof of relevance to MLTT in some fashion in order to solve these problems. There's one solution which I found a paper by Gilbert and others where they talk about extending MLTT with an impredicative universe of strict propositions. And that's quite interesting. But there is a problem in that it assumes stuff like propositional resizing, which we don't necessarily want to immediately assume. We want to try and take a more bare bones approach if we can. So instead, what we want to try and do is we just want to extend the rule set of MLTT with propositional truncation so that we have access to both data types and mere propositions. So just to cover what propositional truncation is very briefly, this is where we kind of force a type to become a mere proposition, i.e. all of its objects are equal. Here are the rules for this. I'm going to have to start going quicker because I'm running out of time. But the key idea is that if we take the truncation of a type, all of its objects are propositionally equal. And then we can use this when we go back to natural language semantics, we can use this to actually prescribe the correct semantics for this sentence. We're taking a truncation of these two different properties. We're no longer counting multiple proofs of the same thing. Fantastic. But there is a problem in that propositional truncation is kind of a very simple higher inductive type. And this means that it's very easy to construct another proof similar to Shulman's, I believe, where we can show that weak equality reflection doesn't actually hold for MLTT with propositional truncation. This is a problem because we want distinctly constructed objects to remain distinct. So we know that MLTT with propositional truncation does solve the counting problem, but we no longer have weak equality reflection. But it's an extension of MLTT. So there should be some subsystem within there that does preserve weak equality reflection. And that the idea is that hopefully we'll be able to use this for its intended purposes with regards to program specification, natural language semantics, and more. And then we can ignore the bits that doesn't have weak equality reflection. So this is something that we're still actively working on. If you have any interests in a really weird application of subtyping, I encourage you to talk to me about what we're trying to do to prove this. But yes, thank you very much for listening.